folks there. Thank you everyone for joining us today, just as we highlight some of the work that we're doing here at Tennessee Tech in the propulsion power and thermal systems laboratory. So today we're going to be discussing some of the multiscale analysis and design of solid oxide fuel cells for the purpose of developing power in space. So with satellite or spacecraft operation in mind. Our funding stream is through AFRL, and our direct funding is managed by the Defense Associated Graduate Student Innovators, DAGSI. So we are appreciative of their support. So just to look at this project from a high level, there are many advantages that fuel cells have over batteries. And so we want to establish an electrical power plant, a power plant that taps into existing fuel and oxidizer supplies on a bipropellant thruster equipped spacecraft. And on the right hand side there, you see a chart that NASA had released outlining some of the sunk cost to the system mass that a fuel cell system has, but you can see there for longer duration missions, the energy density of your bipropellants is quickly going to offset the cost of the gas manifolding, plumbing, and the stack weight that's involved in the fuel cell system. And for longer duration missions that this project has in mind, the fuel cell system would have significant weight savings over a battery system. This also allows a system like this allows you to redesign to meet a certain output voltage and current without changing anything about the chemical storage tank design, and enables perhaps bipropellant thruster and stored electrical replenishment with a single refueling operation. So if you refuel your bipropellant, now you have refueled both your thruster capabilities and your electrical power generation capability. This project is developing solid oxide fuel cells because they are more resistant to poisoning and do not need the expensive catalytic metals that lower temperature fuel cells need. So just kind of an outline of the system concept here. The first system that we've been evaluating is a hypergolic decomposition of a hydrazine and a nitrogen tetroxide bipropellant pair. And you can see from some of the dynamic modeling that we have done in this graph, a comparison of the hypergolic energy density compared to primary lithium-ion batteries and rechargeable batteries, where we've accounted for depth of discharge penalty here. And then you can see even the higher specific, this is an effective specific energy after you account for the weight of the solid oxide fuel cell system and the plumbing and everything, assuming that it is 10% of the total system weight. You can see here the higher specific energy of a liquid hydrogen and a liquid oxygen system as well. So initially we had done some steady state analysis in an engineering equation solver. So anyone who joined the last seminar and heard Will or Jimmy discuss some of the REACH efforts, the DOE REACH efforts, saw him talking about using the engineering equation solver. So we had done some analysis in this as well, and found that for an 18-day mission with a constant 1 kilowatt load, no recharging of a battery or of a bipropellant system available, that the system weight for the fuel cell, fuel and oxidizer would be about 286 kilograms, as compared to 808 kilograms for primary batteries and then 2,700 kilograms for secondary batteries. So again, this highlights, this accounts for even things like the weight of the radiator. You could radiate this amount of heat, 0.69 kilowatts, with a radiator that would weigh about 2 or 3 kilograms. After we had done some of the initial steady state analysis and ease, we moved on to constructing a MATLAB Simulink model of the system as well, including physics for the fuel tanks, the catalyst beds that would decompose, the bipropellants, and a full electrochemistry and thermofluid model of the SOFC. The effort here prefers the system level analysis and simulation over other analysis that we could do like CFD or multiphysics, because this enables us to capture pretty accurately the physics of the system, but we can quickly study and compare the size, weight, and power of integrated systems with many components and do sizing and control analysis. The effort here is to try and optimize the specific energy of the overall system and the volumetric energy as well. So kilowatt hours per liter and kilowatt hours per kilogram. And I don't want to bore anyone, but this is just a breakout of the Simulink model, kind of what's inside of it. And this looks different now, but this is one of the first iterations here. But you can see all the physics that's involved to study the bipropellant tank dynamics, two-phase monopropellant catalyst bed flow, and all of the electrochemistry and the thermal balances that are involved in the SOFC. Just to highlight one component as an example, we developed a catalyst bed Simulink model that would account for a heterogeneous hydrazine decomposition kinetics and the thermal decomposition of ammonia. It accounts for pressure drop in this porous media. So this is a packed iridium nickel catalyst bed that's commonly used in hydrazine monopropellant rockets right now. But we account for all the flow dynamics, and this even has in here temperature and pressure variable thermophysical properties and calculates effective properties of chemical mixtures as well, and also looks at the heat transfer phenomena. So just real quickly here, this is just an example of the hydrazine decomposition. We want to decompose as much of that hydrazine as possible and flow just purely hydrogen, ammonia, and nitrogen into the anode of the fuel cell. So this is just an example of the decomposition that is happening here. And we do decompose pretty much all of our hydrazine here with this design. And this Simulink design enables us to vary things like porosity and particle size as well, along with the heat input can be controlled transiently. So this was using a 20-watt heated monopropellant catalyst bed. So this just elucidates some of the system level, high-level analysis that we can do here at the beginning of the project to outline what components are going to be necessary in order to get this SOFC to run in space. Here you see a Simulink simulation of a 30-minute warm-up of this fuel cell. This is at a set fuel utilization here. You can see the initial warm-up here in these graphs and the respective current voltage profiles, as well as the fuel and oxidizer flow rates. And then one thing that we can do with this type of model is we can optimize the control in order to meet certain targets. So one of the things that we want to do for these high temperature solid oxide fuel cells is we want to minimize the temperature difference across the cell. And so this is a planar fuel cell stack, but with a counterflow flow orientation to it. So the anode fuel and the cathode oxidizer are flowing opposite to one another. And using a MATLAB program that we've developed here, we can interact with the Simulink model and sample different control parameters. And here's a result of one of those efforts where we've tried to minimize the temperature gradient across the cell and minimize the spread of the exit fuel and oxidizer temperature as well. So here we can not only develop an optimized system, but we can have a good idea here at the outset of the control profiles for this system once you would launch it into space. And I've just shown here kind of some analysis that we had done studying the effect of recirculation rates and fuel utilization rates on the maximal temperature difference across the cell. And the manufacturer that we're working with has certain targets for their material set and what type of temperature gradient that they can handle. And so we can get a good idea of our operating range, what fuel utilization and recirculation rates we can use in order to safely operate their cell. Let's see here. So here you see an example of the system power output decreasing with system recirculation, and the power density also decreasing with lower fuel utilization rates in the bottom graph as well. So something that we want to manage is if we have a flow which is orthogonal. So most of these fuel cell stacks, the fuel and the oxidizer are actually flown orthogonal to each other, and so the problem can no longer be reduced by some type of symmetry to a one-dimensional or a two-dimensional model. So we've had to develop full three-dimensional models that will run in Simulink. And so I created a three-dimensional variable time-stepping finite difference code in C that we've embedded into Simulink. It solves the heat equation with variable thermophysical properties, so we can manage, we can look at the electrode, the electrolyte with separate material properties. We can discretize the fuel cell into as many nodes through the depth as we want to, and we impose here heat generation that results from joule heating of the cell and exothermicity from the electrochemical or catalytic reactions. And so this includes all the phenomena that are happening inside of the SOFC. One effort that we would like to implement here is the post-processing using the same finite difference stencil, but solve for the thermal stresses throughout, say, like a warm-up. And again, manage those thermal stresses and look for optimal control paths which keep the fuel cell stresses under, a safe, within a safe operating range. And then we also want to study the effects of, say, compositional gradation within the cell. So there's going to be two types of stresses here: in-plane stresses, which are going to be the result of the way we control the flow across the cell, and then there are going to be stresses through the depth of the cell as well, and that's going to be a result of, say, thermal expansion coefficient mismatch between the electrodes and the electrolyte. And so that we're going to have to approach from a material design standpoint. So this brings us to the next aspect of our project here. We're supporting the Space Vehicles Directorate and the design of the system, but also supporting the Materials Directorate of AFRL in the design of novel electrodes, novel electrode structures. So the way that Wright-Patterson is creating SOFCs right now is they are using an aerosol jet deposition process. By 3D printing an SOFC, now we can control the microstructure, the properties, the electrochemical performance by changing, say, the porosity or the composition throughout the thickness. We can control that microstructure in order that we can impact the performance of the cell and perhaps also reduce the thermal stresses that I alluded to just a minute ago. So for those who are not involved in fuel cell research, there are certain things like the catalytic surface area, the triple phase boundary area. There are things like mass transport within the electrode and the ionic and electronic conduction, which are all very important in the way that the fuel cell operates. And so we have this kind of feedback loop here where we are, on our end, we're using a computational model to show the effects of tuning the powder and the ink properties. And then we're also designing electrode structures and then feeding these inputs to the printing group, who will then send samples to test at Kirtland. And then the ultimate goal is to build a ruggedized SOFC stack. So one that builds upon knowledge that was already used to launch a solid oxide cell into space. We were working with the Oxide company out in Utah. They developed the MOXIE system, which is on board the Perseverance Mars rover currently. Not being run in a fuel cell mode, but being run as an electrolyzer, where it electrolyzes CO2 and develops pure oxygen on board. So we want to take some of their existing knowledge, but then improve the electrochemical performance so that we can perhaps get a higher and enhanced power delivery. So the way that we did this is we created an effective medium model to track the properties through the thickness of the electrode. And we're just assuming averaged values along the transverse dimension. And if we're only controlling the way that these properties change through the thickness, then we reduce our problem down to one dimension and create a boundary value problem. We also wanted to correct some previous errors that were present in the literature when it came to studying functionally graded fuel cell electrodes as well, and build a reduced order model that enables fast and efficient optimization of electrode profiles if we switch our materials or our operating modes. So we don't want to do something like finite element analysis where it might take a few days just to run one test. We want to be able to sample many hundreds of individuals and profiles and come to an idea of a global optimal solution. So here you see just a sample of a few equations that are present in the boundary value problem. So this would be the voltage loss present in the cell, the electronic current density, and the partial pressure or the mole fraction of hydrogen. And then you see their respective profiles coming from the solution of one of these runs. I'm going to, since we're running a little bit short on time, I'm just going to quickly go through here some of the work that we did at Tennessee Tech to guide this process. We sampled the particle size distributions of the ink powders that are being used at Wright-Patt. We've also done a lot of image analysis as well. One thing that we're trying to do is develop a model which uses parameters that can be gleaned just from two-dimensional images. The reason that we want to do this is because it's much easier, much cheaper to use two-dimensional SEM images than try to do full-blown 3D tomography reconstructions of these cells. So we want to right now we're comparing our results to see if sampling across discrete cross sections like this and then adding up a few samples, we approach the same microstructure parameters that we would have arrived at had we done three-dimensional tomography. So here you have on the left-hand side EDX overlay on SEM showing us the phase fractions in a anode, the nickel and the YSZ. And then we can also pull out the measure of the porosity within the electrode. And then we use a randomized line intercept method to derive or to get the particle size distribution of the grains. And then I've worked on some theory here which is really just relevant for the electrochemistry, but it enables us to go from the particle size distribution of the centered electrodes to get back out the percolation probability and the effective ionic and electronic conductivity of the electrodes. And so these things will be functions of the polydispersity of the grains. And again, I know we don't have time to necessarily go through all this. Suffice it to say, we maximize our triple phase boundary, or the length along which these electrochemical reactions are taking place. If we minimize the standard deviation of both particle phases, so for an anode, a nickel and the YSZ, we want to make that as monodisperse as possible, and we want to try and closely align the average particle sizes as well. But as we see from the graph on the right, the triple phase boundary is less sensitive to changes in the smaller particle size. So if phase 2 is twice the average particle diameter of phase 2 is twice that of phase 1, then I can increase the standard deviation of my smaller particle phase and not negatively enhance the triple phase boundary by quite as much. Another thing that we did, just correcting from literature, is some folks had used a dusty gas diffusion model, but this is not, excuse me, they had used Graham's law to decouple the dusty gas diffusion model, but this isn't appropriate under chemical reaction. And instead, we related this to the molar flux, which is going to result from the exchange current density of the electrode, and then came out to this novel expression here, which is somewhat cumbersome, but can be numerically integrated and is going to account for this anisotropic media, where my composition or my porosity is going to change throughout the depth of the electrode. One equation that we've kind of added here to the field. So previously, folks had derived equations for the triple phase boundary and the specific area of like a phase with the pore space from literature. And we have derived this new expression here, which will give me the interfacial area between nickel particles or between like particles of the same phase, or the areas between particles of two separate phases. But I can go into that in more detail if anyone is interested later. So first we did some single parameter optimization where we just tried to minimize the overpotential. And here's just briefly as a result from that on the right-hand side. So starting at an initial guess such as this on the left-hand side, we come to a solution like this on the right-hand side using gradient descent optimization. Just a side note here, I don't have any actual numbers through public release, but we have actually tested a cell like this that had a porosity gradation to it in the last few weeks and saw very, very good results compared to some of the cells that we had previously been testing. So hopefully we'll be able to release that in literature here soon. Another thing that we had done is added a thermal stress model to the electrode so that we can track the thermal stresses, the tensile and the compressive thermal stresses that are present in the cell, just as a result of the thermal expansion coefficient mismatch between, say, a nickel and a YSZ in an electrode. And here you see the various grading profiles, and then on the bottom, a representation of what the MATLAB program is actually computing on. And then here's the profiles flipped. So once we have this included, now we can do multi-objective optimization on an electrode, and we can find a grading profile which will both minimize our the overpotential or our power losses and minimize the thermal stresses that are induced in the cell as well. So here you see just a linear profile is going to give you your the minimized absolute thermal stress, and then a profile like B is going to induce really high degree of thermal stress but have a lot better electrochemical performance. And interestingly enough, individual C here is kind of a balance of objectives. And you can see it's just a homogeneous electrode where the electronic conductor fraction has been minimized down to its what's called its percolation threshold. So the minimum fraction at which you can get particles chained together and able to conduct electricity all the way through. And then we've also done multi-objective optimization where we allowed the solver to change the particle size. And you can see here that the results try to group the particle sizes of the two phases together. You can see that for both individual A and individual B. And then depending on the porosity and the particle size, sometimes your homogeneous cell will still have the best electrochemical performance. So this was interesting for us. We do think that once we start studying electrodes with material properties that are more similar, here we have a nickel and a YSZ where one is just an electronic conductor and the other is solely an ionic conductor. If we have mixed conduction in some of the materials, then we expect that gradation might improve the cell performance by a little bit more. But this is good for us to validate these things through theory before we really begin printing. Again, just special thanks to AFRL and the Seedlings for disruptive capabilities, and DAGSI for their support on this project. And it looks like the grant number got cut off there. But does anyone have any questions? Again, I want to thank you for your attention this morning. And if you want to know anything else about our work that we do here at Tech, please visit our website and contact me or Dr. Roberts and let us know if we can help in any way. Any questions on the presentation this morning? I know that was quite a bit to run through.
Aaron,
Hi, Aaron.
oh, go ahead.
No, go ahead.
This is Doug. This a nice talk. Good work. I'm glad to see it. You know, when we started this, we were looking at the gradients, so I'm delighted to see the progress there in the whole concept of gradients. If we take what's called an inverse engineering, often called an inverse engineering approach, and we said, okay, currently, if we design a fuel cell system, we get this specific power, this power per mass, this power per volume. And then if we started saying, okay, we want this target specific power per mass and volume. And we went backwards and said, okay, what do we have to do? There's some things at the system level, and obviously, and then some things maybe at the materials level. Any idea on at the system level what might be achievable? Are we looking at a 50% improvement over current stuff, state of the art, a doubling, a 10x? Any thoughts or insights on that?
Well, part of that is difficult to answer just because you know, an SOFC system has not been flown in space before. So I guess my goal is to take that 1 kilowatt number that we've been working with and then just try to minimize the mass and the volume for that 1 kilowatt system. Looking at the inverse problem, we have begun to study that a bit. Looking at the electrodes, which perform better, and based on some of the most recent printing and testing results, we do think that we could decrease the stack mass by about 30% or so, which would be great. But I do know from the MOXIE system, the stack weight was pretty low compared to all of the packaging and the thermal insulation, everything that was involved. So it might be best just to increase the power density of the cell instead of, you know, increasing the efficiency or decreasing weight. But those are some problems that we're looking into, and that was part of the impetus behind building that real-time system level model in which we can discretize the fuel cell. And so we might want to ask, well, if I want to say minimize my risk of delamination during warm-up, and I use this gradation, and then I actually run that in the system model, then I can see that the generation of thermal stresses there that would be present. So that might be one of those things where the operation of the cell and how much fuel and oxidizer we end up wasting running through some warm-up scenario might have a much greater effect on the overall system weight. So some of this work that we're doing to de-risk delamination might have a big impact on how rapidly we can warm up the stack, right, and thereby use less oxidizer and fuel.
So yeah, because I'm clearly focused there on the swap, the size, weight, and power, yeah. And a lot of your effort is more on the stresses for startup time. And I'm thinking beyond these type of fuel cells, but also any thoughts on lifespan?
Lifespan. Without giving too much away, I guess I could say that again, the company that we're working with, Oxide, especially as we explore their material set that they're working with, they're very confident that they're not going to have, say, thermal or electrochemical degradation over anywhere from 2,000 to 5,000 hours.
Yeah, no, I was not actually looking at oxygen. I was thinking of
Or
another application where fuel cells are used and the lifespan just isn't there. So we can talk about that
okay,
offline.
okay.
Thanks.
Yeah, Aaron, this is Fernando. Very nice presentation. You know, just to continue along Doug's lines, I think that what you're doing is extremely important for fuel cell degradation because one of the primary mechanisms of solid oxide fuel cell degradation is thermal stress related and cracking due to that. There's definitely some interdiffusion problems, but I think that those have been pretty well solved, and the very long lifetime of tubular fuel cells, which don't have the as much where the interfacial stresses are lower, because you essentially have tubes which are allowed to expand and contract quite readily in most of those designs. They have very long lifetimes, over 20 to 40,000 hours. So I think that focusing on the mechanical stresses and thermal stresses which are induced is extremely important. But I have another question. How confident are you in the kinetic data which you have for the electrochemical reactions? Because my feeling is it's still it's very materials dependent, and it seems it's also that respectable groups have gotten very different data, and I think it may be due to the complexity of the transport being interwoven with the charge transfer kinetics. Thanks.
Oh, yeah. So as far as the terms for the exchange current density that we're using, those are literature values that I'm using for nickel YSZ, and then for the cathodes, currently those are also taken from literature. We are doing some EIS testing right now and hope to get some of those numbers ourselves, especially for the new materials that we're going to be implementing.
Yeah, because one of the comments which some of the longtime researchers like Mogensen in this area is that while the kinetics, the charge transfer kinetics look like that they fit a Butler-Volmer model well, but it's not due to the fact that it's due to the electron transfer reaction itself. It's due to the vacancy transport mechanisms within the mixed conducting electrolytes and the solid electrolyte itself. So you get that same exponential over potential type of behavior, current density with increases exponentially, but it's not due to electron charge transfer. That's not the rate limiting step. And probably for your model, it doesn't really matter as long as it accurately models the polarization behavior of the fuel cell. But it's pretty intriguing that even after all these years, there's still quite a lot of debate on at the fundamental level what is governing the charge transfer kinetics within these systems.
Yeah, so I guess that will have an effect, but I could see its effect on the model just being linear, since that term is being applied throughout the cell. I don't necessarily see it. The model is capturing more the effect of not the rate limiting reaction, but of the respective electronic and ionic current densities and the percolation at a given composition through the depth. So, but we can talk about this more offline. But especially for the cathode, I am using a modified Butler-Volmer equation, which assumes triple phase and two-phase reactions happening in parallel. And then the exchange current density is going to be an Arrhenius form.
Yeah, and that makes sense. And using that modified Butler-Volmer type of analysis. There are some researchers who'll take my head off if I use the word Butler-Volmer, because they say that is solely about electron transfer, not about, there's no diffusive transport within the cathode material considered, right, in the Butler-Volmer analysis. But getting back to the practical world, I think that fits very well in giving you the ability to model different materials such as the lanthanum, strontium, manganetes, which have almost no oxygen diffusion, right? The diffusion is very low within the material, versus lanthanum, strontium, cobalt, iron, oxide, where there's significant oxygen diffusion. So there's a significant two-phase interfacial effect. So that's very good. I just caution you when you present that you don't say that we're implying that this is all just about electron transfer as a rate limiting step.
Okay. So within, I guess it's opaque here on this slide, but this this exchange current density term here is also partial pressure or mole fraction dependent, if that's what is that partly what you're referring to?
Well, what I'm referring to is that while the form of the equation is very accurate, the underlying physics that the Butler-Volmer theory is just about was based on electron transfer at the triple phase interface only. That's the kinetic rate limiting step for that reaction. And the subsequent research has shown that electron transfer is incredibly fast at these temperatures. And it's not necessarily the electron transfer, it's more it's probably the diffusive transport or at the cathode materials, which is governing the rates, or the dissociation reaction at some temperatures, which are governing the kinetic rates. And they all have these Arrhenius type of behavior. So the Butler-Volmer-like equations fit very well, but some people in the solid oxide field get very offended when we keep using the word Butler-Volmer, because they believe that that term should only be used for electron transfer. So I've used in the past Butler-Volmer-like, or carries the form of a Butler-Volmer equation, but it is not. We're not assuming that the reaction is electron transfer reaction is the rate limiting step at the triple phase interface.
Yeah.
Hey, Aaron, this is Gami. Can you hear me?
Yes, I can.
Yeah, nice to hear from you again. A really nice presentation. So I had a question on slide 10. Now you're showing the modeling of hydrazine decomposition, I believe. 7. And you're showing a Arrhenius rate constant for hydrazine heterogeneous decomposition. May I ask, where do you get that activation energy from, or is that something you adjust and get the profiles on the right side?
This activation energy is again from literature. I can send you the paper if you want. I think we might have had this discussion once before. And I hope I can go back and look at my model and make sure that there's not a misprint here.
Okay.
But this is from some
it kind of
monopropellant decomposition experiment.
But I would like to see the reference.
Okay.
Now, it is well known that hydrazine can be decomposed on a catalyst to hydrogen and nitrogen. Now, on I think slide 10, was it? Yeah, slide 10. Now, on slide 10, or on 11, I think. Yeah, So for the oxidizer, it is much more problematic. You know, the actual oxidizer in the spacecraft is nitrogen tetroxide or NO2. Now, I assume that in this simulation, you have assumed some mole fraction of this nitrogen tetroxide decomposing to nitric oxide, and oxygen.
Yes.
I mean, we are working this problem really hard. What kind of catalyst will produce this? Because this is essentially the bottleneck of applying this solid oxide cell. If you cannot decompose the nitrogen tetroxide effectively, then you have a problem of corrosion on your cathode. So nitrogen tetroxide is highly corrosive. So before you can expose your cathode to an oxidizer, you have to really reform this oxidizer to a more, perhaps, less reactive mixture, such as nitric oxide and oxide.
Yeah. So our proposal.
Sorry, before I finish, then you also have a problem that immediately when you have nitric oxide and oxygen, it is going to go back to nitrogen dioxide. So this is a very complicated problem to solve. So have you looked into the literature of what kind of systems might be able to do this conversion? Or at the moment, is it just a guess in your model?
Yeah, well, this is our proposal currently is that you would have basically a heat exchanger setup here, and again, I don't have release on this, but using the exothermicity of, say, the hydrazine decomposition,
right,
we can heat up the NTO flow as well, up to a temperature at which the NO2 decomposes as well. Through our own kinetic analysis, I used a Monte Carlo solver, and looking at literature as well. Some of the old NASA reports, Airjet Rocketdyne. We are going to have some remainder of NO at the SOFC temperatures. Some remainder of nitric oxide in the cathode stream. That's what I had seen. But I know that that the group that we're collaborating with at Kirtland UNM is currently looking at this problem as well and studying NOx decomposition on cathodes.
All right. One last comment. Could we have a copy of these slides somewhere available?
Yes, we're going to upload them to the website here after today.
Yeah, otherwise really nice modeling and simulation.
Thank you.
Hi, Aaron. My name is Hossein Ghazalak. I'm from Fuel Cell Energy.
Hi.
Dr. Rory asked me to join this seminar. Pretty good presentation. I gotta admit that you've done quite a bit, and it's a lot of material, even for a PhD, all the way from design in terms of system design, going all the way to stack design. One of the questions: what is the assumption on your anode thickness?
Well, it depends on the configuration of the cell. We have been looking at anode-supported cells with electrodes up to 400 microns thickness, down to, I think, 250 was the minimum. Let's see here. Let me go over to this slide. This was optimization on a 250 micron. Well, there we go. Yeah, 250 micron electrode. Now we are currently looking at electrolyte supported cells primarily. Something else that we had done with the model is we didn't grade the profile or anything. We just studied homogeneous electrodes, and I allowed the gradient descent algorithm to find optimal thicknesses. So it was able to vary it, and it arrived at a length of about, or thickness of about 20 microns, 20 to 25 microns for the anode, and I think it was 30 microns for the cathode, which again, if you look at some experimental results, that has been verified. But those are the numbers that we've been sticking with in our electrolyte supported cells. So 20 to 30 microns.
Oh, electrolyte support, yeah, right.
Yes, yeah.
But so there are so many questions. One of the slides, I just want to make sure that you corrected. You talked about when you were looking at the composition of the anode itself. You talked about particle size, contribution from
Yes.
zirconia, and you showed nickel. That really should be nickel oxide.
Yes.
So,
On which slide?
you tell me, I don't remember the number, but you talked about composition of the particles, because typically, especially for what you call nickel YSC, the starting point to fabrication is nickel oxide.
Oh, yes. When we were doing the particle size analysis, yes.
Right. Yeah,
nickel oxide here.
Yeah, but there was one slide that you showed nickel and zirconia particle size, and you said nickel instead of nickel oxide.
Oh, well, yeah, so there's going to be a difference between the centered and reduced final microstructure, which is going to be primarily nickel. So the nickel oxide gets, yeah.
Yeah, but in fabrication, starting point, you use nickel oxide.
Yes, yeah. So I'm sorry if I didn't make that clear. We are assuming that we're trying to track correlations between the initial green body and then the final microstructure, but the simulation of that centering process would be a whole nother project unto itself.
Right. So that's so when you were doing the study of what's the optimum structure is, your starting point was at the fabrication level.
Just before we had got any SEM images, I used that as a starting point, and then I assumed a reduction in density from the nickel oxide to the nickel, and so I just assumed just a volumetric reduction corresponding to their to the density of nickel oxide to nickel. So yeah, I accounted for that in the model using the rough numbers at first, and then once now that we have these SEM images, I just use these final particle size distributions. But the theory here, in reference to the polydispersity of the grains, that applies to the final microstructure.
Yeah, I understood, because you're looking at the percolation of density, so that there is a minimum of nickel or nickel oxide you need to start with, but there is also a maximum. So I'm wondering if your optimization can. There's only a very narrow range, actually. Practically, you can use the concentration between the two. I mean, typically the median 50-50 is rule of thumb, is the right percentage of the two, no matter what the model shows. but you could go maybe 40-60 all the way to 60-40. That's the range practical to look
Yeah.
at it. And then of course there's the flexural strength of the whole thing because it's going to be used as a support. All right. Yeah, as I
Yes.
mentioned, there's a lot of different topics you have worked on, and we can discuss it for an entire day. So leave it as it is. Thanks.
Okay. Yeah, thank you.
Yeah, Aaron, I got to leave for a 1 o'clock, but I'm very impressed with your modeling. It's just an excellent merge of some very good basic work, and I'm particularly the Simulink models and just throughout your whole presentation. So you're certainly doing some excellent work. But I got to leave now. Thank you.
Okay, I appreciate it. Thank you.
Sure.
Anyone else have any questions?
Hi, Aaron. This is Ted Orn with Special Power Sources.
Yeah.
I just had a question about the pattern electrode work. It's an interesting approach, but obviously there's a cost associated with more complex manufacturing. I don't know if you've seen or if you're aware of any cost trade-off studies that would talk about the benefits versus the costs. Just curious if you know anything along those lines.
We haven't done any studies like that in reference to cost. Once we arrive at some designs that have been verified through experiment over and over again, then I guess some of that work that I already talked about in reducing, say, the number of cells in a stack, that you could use to look at final cost for the stack. From the manufacturing perspective, some of these graded structures could also be produced through other means as well. So say like a dip coating process, or perhaps screen printing. But you'd have to make batches of all different compositions of ink, which would be kind of problematic. The advantage here is that we just have the aerosol jet, and we have two separate inks that we can blend as we deposit. So that's the advantage. If this was going to be turned into an assembly line process, I could see an assembly line where you have rows of jets, each of which are spraying different compositions, and perhaps you print a cell in that way. Just run it through, print 20 layers or something like that. But as you can see here for the nickel YSZ, we found that at least the compositional grading is not all that beneficial. But we think that's due to the disparity between the respective conductivities. So you just want to minimize the electronic conductor down to its percolation threshold, and leave it at that. But as far as the porosity grading is concerned, I could see that perhaps being done through a screen printing process. Some of the prints that we've done, we've just broken the electrode up into like 3 or 4 discrete layers and approximated it that way.
Aaron, just to comment, Doug again, your comment that the porosity, your comment on the change with porosity goes along with, I think, Fernando's comments that, like, Butler-Volmer is the electronic, and you're not seeing the electronic effect. If you were seeing the electronic effect, you'd have different results there, I think. But that, in other words, that's affirming what Fernando said, I think.
Okay, yeah. The porosity is also going to feed into the multi-component gas diffusion as well.
All right. Does anybody have any other questions? Well,
It was a very good presentation.
Thank you. And this is what we have through public release. So we have newer work going on right now that we're eager to